For us, life unfolds on human scales. Miles, feet, inches. But beneath the surface of things is another realm, a billion times smaller than we are. A dimension that holds the secrets to understanding our world. What makes steel strong? Why ice cream is delicious? What makes life possible? Secrets that help us create what we imagine.
The human creativity of chemistry, there's just nothing more beautiful than them.
This is the realm of chemistry, and these are its greatest discoveries. Ancient Greek philosophers believed there were just 4 elements: earth, air, fire, and water, and that air was the underlying element, a single substance responsible for the makeup of everything in the world. Centuries later, Leonardo da Vinci was among the first to suggest that instead of being an element, air might consist of 2 different gases. It remained a mystery until our first great discovery. England, the latter part of the 18th century. Clergyman and sometimes scientist Joseph Priestley conducted a series of experiments searching for new airs, what today we call gases. To find out more about what Priestley was up to, I paid a visit to Arnold Thackeray, president and historian at the Chemical Heritage Foundation in Philadelphia, Pennsylvania.
And Priestley wrote and wrote and wrote on every subject that you've ever thought of. He wrote about history, he wrote about religion, he wrote about politics, he wrote about science endlessly. And Priestley was the man who knew everything. He would tell you the practice of it, the history of it, the theory of it, and he was quite literally the man who knew everything.
But along with everything else, Priestley did this famous experiment, right?
That's exactly correct, and there are 2 things that go into that experiment. The one is mercury, this strange substance that's simultaneously a liquid and metal, and that's just crazy. I mean, who ever heard of a liquid metal? And so it was really puzzling, what is this thing? And people were fascinated by it, and so they wanted to explore it. And of course, the other thing that went into it was the technology to deal with gases. And here in Priestley's experiments and observations on different kinds of air, we have the technology of collecting gases over liquids.
In tubes that you could see through.
Exactly. So you can see the gas, you can see what's happening to the gas, and now you really are in business. What Priestley does is he takes a burning glass to give him heat, a lens. He focuses it on this orange powder, the mercuric calx. He heats it, it changes into this metal mercury, and a gas comes off. But Priestley doesn't really realize what it is that he's found.
The answer would emerge in 1774, after Priestley paid a visit to Paris and shared the story of his discovery with another scientist, Antoine Lavoisier.
Paris is a marvelous place for Priestley to visit because Antoine Lavoisier is in Paris, talk of the town, doing the work that will end up as his elementary text on chemistry. And Lavoisier who is also mucking about with gases, hears what Priestley's done, is fascinated by the report of this new air, decides he'll repeat the experiment. He has lots of apparatus, better apparatus. He's a meticulous experimenter, and among other things, he weighs things. Lavoisier, by weighing, says something is being emitted. He calls the thing emitted oxygen. He rewrites the whole script of chemistry, and he creates a list of elements that we still use today: oxygen, hydrogen, sulfur. You can correctly say that Priestley discovered oxygen, but Lavoisier invented it. So with Priestley's experimental work on gases, with the discovery of oxygen, with Lavoisier's articulation of a system of language, we have the whole conceptual scheme in which 19th century academic work is built, 20th century industrial innovation. We have pharmaceuticals, we have biotechnology, we have cell phones, we have plastics, that's exactly right. And all these things begin with the discovery of oxygen. That's where it starts.
That's a lot to breathe in. In the early 19th century, a British schoolteacher named John Dalton was hard at work, pursuing his fascination with chemistry, which would lead to our next great discovery. Dalton's experiments showed that the known elements such as oxygen, hydrogen, and carbon combined in definite and constant proportions. From his calculations, he hypothesized that the elements must be made up of smaller, invisible pieces of matter with relative and distinctive weights. He called these pieces of matter atoms. So, what did Dalton discover?
Dalton's great discovery was what he called the relative weights of ultimate particles.
Ultimate particles.
That's what he called it. It's a lovely phrase. Later on, when he went public, it becomes atomic weights, and we know it as atomic weights, but it was ultimate particles.
So he used the word atoms.
He used the word atoms. The idea of an atom, of course, goes back to Democritus. The problem is, it's an idea, is it any use? And Dalton was the man who made the idea useful. That was his great contribution.
From his work, Dalton developed what came to be known as his atomic theory, a revolutionary new system that defined the relationship between atoms and the elements.
And it's an enormously simple system, and Dalton thinks very simply, very visually. Here are the elements, here are the weight of the elements, here are the complex molecules, and it's a wonderfully effective system. It connects the thing that chemists can do, weigh things in balances, with the things that you can't see, the ultimate world of atoms. That's genius.
How important was Dalton's discovery? His atomic theory helped generations of scientists further unravel the mysteries of the atomic and molecular world, including our next great discovery. In the early 1800s, French chemist Joseph Gay-Lussac was conducting a series of experiments designed to study Dalton's atomic theory when he observed something odd. When he combined equal volumes of different gases and measured their reactions, the gases often produced twice the volume than he expected. How was this possible? The answer was provided in 1811 by Amedeo Avogadro, a physics professor at the University of Turin in Italy. While studying the results of Gay-Lussac's research, Avogadro had an insight. At the time, it was believed that gases were made of single atoms. Avogadro realized this assumption was wrong. The gases were made of multiple atoms, what came to be known as molecules. The realization that atoms could be rearranged to form molecules was the breakthrough that enabled scientists to move out of the chemistry dark ages and begin systematically creating new compounds. Our next great discovery occurred in the 19th century, when many chemists believed that organic substances from organisms or living things were somehow different from inorganic substances, from non-living things. But that was about to change. In 1828, Friedrich Wöhler was working in his lab when something caught his eye. Wöhler had placed two inorganic chemicals in a beaker, potassium cyanate and ammonium sulfate. Now when he looked at the beaker, it contained a gram's worth of small, white, needle-shaped crystals. What made this remarkable was that Wöhler thought he'd seen these exact same crystals once before, but with an important difference. Those crystals had been organic. He had crystallized them while studying the chemistry of various substances found in urine. To make sure he wasn't mistaken, Wöhler analyzed the new crystals. There was no mistake. These crystals were the same as those he had isolated before.
He had made urea, which was something that had come out of a living thing. He had made it out of inorganic substances. Later he said, in a personal letter, not in the paper he wrote about it, that I have made urea without a kidney. And he knew what he had done.
Meet Roald Hoffmann, winner of the 1981 Nobel Prize in Chemistry for developing a theory to explain organic chemical reactions. So why is this discovery of artificially making urea, why is that a great discovery?
You know, there comes a time when you need a discovery, and it's sometimes a single one, to cross a border, to break down a wall. This is what this discovery was. Wow. It's not that it was so important in and of itself, but at the time that it came, the simple making of urea out of two inorganic chemicals, when it came, it caught people's attention. The whole story of the discovery is about the underlying basis, the building blocks of all matter, organic and inorganic, being the same, atoms.
If these Lego bricks had existed in the early part of the 19th century, chemists could have used them to help illustrate something they were seeing in their experiments. A phenomenon that led to our next great discovery. The atoms of particular elements, such as sodium and chlorine, seem to combine with each other according to fixed ratios. It was this combining power of atoms that inspired German chemist August Kekule to develop a system for visualizing the chemical structure of various molecules. Kekule represented the atoms by their symbols, then added marks to indicate how they bonded with each other, like links in a chain. It was a simple yet elegant formula. Chemists now had a device for clearly illustrating the chemical structures of the molecules they were studying. There was just one problem. Benzene was the only known chemical that would not fit Kekule's formula. Benzene's chain of carbon and hydrogen atoms required more combining power than the formula would allow.
And all these organic chemistry professors are puzzling about it and offering different explanations. And one of them, August Kekule, sitting by the fire one evening, falls asleep and starts to dream about a snake. And if you think about a snake, what Kekule dreams of is the snake catches its own tail. And if you think about this, maybe the thing is a ring. And that gives you an answer to the puzzle.
The 6 carbon atoms of the benzene molecule weren't linked in a chain. Like the snake, they formed a ring, each with a hydrogen atom attached, with alternating single and double bonds. Within a short time, Kekule's insight was confirmed, and its effect was revolutionary. Chemists knew that all organic substances contained 1 or more carbon atoms in their molecules. With Kekule's discovery, they now had the underlying formula to explain how carbon combined with other molecules to form a world of chemical compounds. The modern era of organic chemistry was born. Now, with this thing being so simple, that is to say, the snake bites its tail, why is this considered a great discovery?
Here is a recipe for new drugs, new medicines, new understanding. If you go back in time, in Dalton's day, a couple of hundred compounds. Soon it's a couple of thousand. Soon it's 10,000. Astonishing. Soon it's 100,000. Last year, 15 million new compounds were registered, all built on this simple template. This is a work of genius.
In 1869, a Russian chemistry professor named Dmitri Mendeleev was writing a textbook for his students when he began to wonder how he could best explain to them the 63 elements that were known at the time. To help formulate his thoughts, he constructed a card for each element. On each card, he wrote the name of the element, its atomic weight, its typical properties, and its similarities to other elements. He then laid the cards out like a game of solitaire and began arranging them over and over, searching for patterns. Then came the moment of discovery. Before him was something extraordinary. The elements fell into 7 vertical groupings. Each periodic grouping had members that resembled one another, both chemically and physically. Mendeleev had discovered the periodic table of the elements, a map showing how all the elements related to one another. A map so precise that Mendeleev believed he could also use it to predict the existence and properties of 3 elements no one had yet discovered. One would be like boron, he said, one like aluminum, and one like silicon. Eventually, the elements were discovered, and Mendeleev was proven right.
There was actually a little bit of controversy because a German chemist named Lothar Meyer had come up with roughly the same idea. But Meyer didn't quite have as much courage. So that's actually an interesting thing. Here is this German who comes up with the same idea of periodicity, of which there were hints already before, but he doesn't make the predictions that Mendeleev does. So here we see the power of a risky prediction in having people accept a theory. There is nothing more powerful than making a prediction that's not obvious.
And then have it come true.
And have it come true. Mm. The periodic table is our icon. I mean, it's what we associate with chemistry. You go into any chemistry room, you see it.
Why is the periodic table of elements significant? It forever changed the way that everyone would learn and understand the elements. The periodic table of elements is to chemistry as notes of music are to a Beethoven sonata. In honor of Mendeleev, his name is now literally attached to the periodic table. The element 101 was named after him. It's called Mendelevium.
It's not only chemists who like the periodic table. I hear you carry one around.
I do carry one, yes, sir.
Show me.
You never know. And I seem to use it a lot.
Let's see.
It's a small one.
So I'm going to give you a test. What is under nitrogen in the periodic table?
Nitrogen is 7.
Yes.
I have to think a second.
Under
sulfur.
No, you're wrong.
Oh, God. That's
Close.
why I carry
You're
the thing.
one off. It's phosphorus.
Oh, phosphorus.
Phosphorus
15.
is right.
Phosphorus is 15?
Yeah, you have to add 8 at that point.
See, that's why I carry it. I can't remember. So it's 7 plus 8, 15 phosphorus. Okay. There's a pattern there. I get it now. At the turn of the 19th century, electricity was all the rage. People were busy making batteries and connecting them to just about anything to see the reaction. Electricity was like a new kind of fire. One of the great battery junkies of the day was Humphrey Davy, a self-taught English chemist. In 1807, Davy was performing a battery experiment in his lab. He melted some potash, a mineral found in the ground that also forms in the ashes of wood. Chemists had speculated that potash was a compound of several elements, but had not been able to prove it. Davy wanted to see if electricity might provide the answer. He ran some wires from one of his biggest batteries to the melted potash. Pure potassium began to emerge. Davy had discovered the power of electricity to react with chemicals and transform them. Eventually, electrochemistry led to the rise of the aluminum industry, the production of semiconductors, solar panels, LED displays, even rechargeable lithium batteries. In the 1850s, Robert Bunsen and his research collaborator Gustav Kirchhoff conducted a series of experiments to determine why substances emitted specific colors when placed in a flame. The color they determined indicates what elements are present in the substance. For example, if sodium is placed in a flame, they observe shades of yellow. Copper, shades of green. Strontium, shades of red. That was a good one. While watching the experiments, Kirchhoff was reminded of how a prism spreads light into a rainbow of colors. So, using a prism and the pieces of a small telescope, Bunsen and Kirchhoff built the first spectroscope, an analytical device they hoped would help them see the spectra coming from heated substances. And it worked. As an element was put into the flame of a Bunsen burner, the light from the heated substance passed through the prism of the spectroscope, where it then spread into a ribbon-like spectrum of colors, riddled with dark lines. The combinations of bright colors and dark lines were like barcodes indicating what atoms were present. When burned, each element produced a completely unique spectrum. Using their spectroscope, Bunsen and Kirchhoff were able to discover two new elements, cesium and rubidium. One day, Bunsen and Kirchhoff decided to test their invention with sunlight. It produced a spectrum that featured two lines that were identical to those in the spectrum produced by sodium. Bunsen and Kirchhoff had discovered the presence of sodium in the sun, 93 million miles away. Suddenly, scientists had a tool to help them study the chemistry of the heavens.
Liftoff. We have liftoff.
Today, the legacy of this great discovery lives on in the exploration of space. A form of spectroscopy is being used to study the atmospheres of planets, to search for signs of water, signs of life. Our next great discovery is the story of Joseph Thomson and the electron.
So here we are.
So everything that we can see is made of chemicals.
That's right.
What's the future?
And they're all bonded through electron interactions.
Thank goodness.
The future.
To find out about it, I paid a visit to Harvard University. Dudley Hirschbach is a professor here and winner of the 1986 Nobel Prize in Chemistry for his research into the dynamics of chemical elementary processes. So, Thomson didn't discover the electron.
Well, it's of course said that way, but he didn't discover in the sense that he said, Eureka, I've got this thing, here it is. He did an experiment that allowed him to measure the ratio of the charge, the electric charge, to the mass. And then later he was able to get a rough measurement of the charge and therefore show that the mass was very, very small. It was about 1/2000th of the mass of the lightest known atom, hydrogen atom. So it showed that he could extract in the experiment a very small piece of an atom. Well, that was a tremendous shock. People didn't
Pun
imagine.
intended.
Yes, yes. Electrical piece of an atom. It was a very small part of the atom.
At the time of his discovery, Thomson was a professor at England's University of Cambridge. He was using a device called a Crookes tube in his experiments.
I happen to have here a little apparatus that's akin to the one that J.J. Thomson used in 1897. It's called a cathode ray tube, just an evacuated little glass cylinder with some electrodes. And we can hook this up and show the key points of his experiment.
A replica of the first CRT.
Yeah. It's the first cathode ray tube. It's ancestor of the television tube, as a matter of fact. You do the last one, and we should get a stream of cathode rays or electrons going there, and it'll show up. A few of them bang into this phosphor-coated piece of cardboard there. Here, I'll give you a magnetic field you can use to deflect the electrons.
When Thomson exposed the stream of cathode rays to a magnet, the stream would bend. Since magnets can only affect matter, this meant the stream of rays was composed of some kind of electrically charged substance called radiant matter. After many hours of observing and measuring, Thomson realized he'd found the first subatomic particles. The ray was a stream of electrons. It was a revolutionary discovery.
Some years later, a student of Thomson, Ernest Rutherford, was able to show that the positive charge in atoms, which was, of course, had to be there to balance the negative charges of these little electrons that were scooting around, was localized in a tiny, tiny nucleus, 100,000 times smaller than the size of the atom. And so almost all the mass was, of course, in that nucleus as well, because electrons are so light.
And that's still the model we have today, right?
That's the basic model for atoms, and of course the key to understanding everything involving atoms.
Like chemistry.
Like chemistry in particular, that's right.
Scientists were just beginning to discover the anatomy of the atom. Now they wanted to understand its behavior, specifically the mechanism that enabled the atoms of certain elements to combine with the atoms of other elements to form new substances. In the early 1900s, American chemist Gilbert Lewis developed a model of the atom that provided an answer.
It is he who explained that electrons in atoms, and chemistry is about electrons, it's not about nuclei, that the electrons in atoms went in shells around the nucleus.
In Lewis's model of the atom, each shell allows only a maximum number of electrons. Lewis theorized that two chemical elements might combine to form a compound when they give up or accept electrons from their outer shells. For example, on their own, sodium and chlorine are hazardous. But when a single sodium atom gives up the electron from its outer shell, and a single chlorine atom's outer shell accepts it, this exchange allows the two to bond and form the compound sodium chloride, table salt. Gilbert Lewis's theory was an extraordinary breakthrough. It enabled scientists to begin making chemical compounds, millions of them, compounds that have shaped the face of modern life. Our next great discovery started in the 1890s with the discovery of an unknown radiation called X-rays. It caused a sensation, and scientists immediately began looking for other substances that emitted strange, perhaps valuable forms of radiation. Over the next several decades, a number of scientists investigated the phenomena and together ended up shedding light on one of the great scientific sleuthing episodes of modern science. French physicist Henri Becquerel made the first significant breakthrough. In 1896, he conducted a series of experiments to see if various minerals emitted radiation. One of the minerals he happened to test was uranium. Becquerel's technique was to place different objects on top of an unexposed photographic plate, still wrapped in protective black paper. He would sprinkle the uranium onto another piece of black paper, then enclose the object between the uranium and the photographic plate. Later, Becquerel would develop the plate, and without fail, a ghostly photographic outline of the object would appear. From these experiments, Becquerel was able to prove conclusively that he had found a source for the mysterious radioactive rays that everyone was looking for. That source was uranium. From Becquerel, the investigation of radioactivity was taken up by Marie Curie. Curie and her husband Pierre undertook the job of isolating whatever elements were responsible for the radioactivity in uranium ore. For 2 years, the Curies boiled, sifted, filtered, and processed several tons of uranium ore. Finally, they succeeded in isolating 2 new elements contained in the ore, which they called polonium and radium. Marie Curie concluded that radium was 1,000,000 times more radioactive than uranium. More importantly, she determined that the mysterious form of energy which enabled radioactivity to penetrate other materials was not the result of a chemical process, but seemed to be atomic in nature. Unfortunately, her discoveries came at great cost. The dangers of being exposed to radioactivity were still unknown at the time, and in 1934, Marie Curie died of leukemia, believed to have been caused by radiation poisoning. Even the notebooks that she used to record her observations are still considered too radioactive to handle. It was the atomic nature of radioactivity that eventually attracted the interest of physicist Ernest Rutherford, whom we already met in the discovery of the electron. Rutherford found that radioactive material goes through a natural process of decay. As it moves through the process, the radioactivity spontaneously emits unstable and highly charged energy particles with the power to penetrate matter. Rutherford called them alpha and beta particles and gamma rays. Since those discoveries, we've learned a lot about radioactivity, the dangers as well as the benefits. Radioactivity has given us medical imaging, a treatment for tumors, a method for calculating the age of the Earth, and a power source for our spacecraft to explore the solar system. Even some smoke detectors contain a small amount of radioactive material called americium, which helps create a steady electrical current. When smoke particles disrupt that current, it triggers the alarm. Centuries ago, alchemists set their sights high. They sought infinite wealth and immortality through miraculous transformations of matter. They came up with useful tools and glassware, but not much else. Chemists, on the other hand, set their sights a bit lower and ended up changing the look and feel of the material world, as did our next great discovery. In the 1860s, John Hyatt, a printer and amateur chemist in Albany, New York, made news when he discovered a way to exploit the long, stringy molecules of cellulose found naturally in plants and created the first plastic. 50 years later, Belgium-born chemist Leo Baekeland took the next step in the discovery process.
One of the great pioneers was Leo Baekeland, who made a polymer called bakelite. The usual thing, chance favoring the prepared mind. He was mixing things, but he knew how to explore them. He saw the interesting properties of this.
From two chemicals derived from coal, Baekeland discovered the world's first fully synthetic plastic. And the landscape of the 20th century was forever changed. What exactly is a plastic?
Plastics are polymers. So what are polymers? Polymers are long chain molecules, not individual molecules that are then clumped up into a solid of some sort. They're really molecules that extend out very far. Chains of carbon atoms, sometimes with some other elements in them. So what are the advantages? Well, it's moldable. You can pour it in some liquid form into some mold. Strength, well, it's not bad. You can make bulletproof vests from plastics. And we've certainly seen that in terms of fibers, they can mimic or even surpass the properties of natural fibers. No fisherman in the world is going to go back to having nets out of cotton, you can bet. Those nets are going to be out of nylon.
So would you say the discovery of plastics is a great discovery?
We have science making polymers, making nylon, making rayon, which has a natural starting point but is modified into a polymer, making plexiglass or polyethylene. Those are the structural materials of our civilization. I think polymers are, in that sense, an example of the human creativity of chemistry. There's just nothing more beautiful than them.
This single gram of black powder costs $500, about 30 times the price of gold. Remarkably, it's a special kind of soot made of molecules called carbon nanotubes. Each nanotube is about 1/1,000,000th of a meter in diameter, thinner than a strand of DNA, yet filled with a world of promise that has a lot of people excited, including a scientist who helped discover them. Richard Smalley is a professor of chemistry at Rice University in Houston, Texas. In 1985, he and fellow chemists Robert Curl and Harold Kroto were studying chemical conditions in outer space. Using sophisticated laser and spectroscopic equipment, they were searching for evidence that might help reveal the chemical nature of interstellar matter. Instead, they found something else, for which they would share the 1996 Nobel Prize for Chemistry. What exactly did you discover?
Well, in 1985, over a period of a week, we discovered that there was one special cluster of carbon atoms that had precisely 60 atoms that was magic. It was specially stable compared to any other cluster. And we wondered why.
Smalley, Kroto, and Curl named the new molecules buckyballs, after Buckminster Fuller, the architect who designed the geodesic dome. What they'd really discovered was a whole new class of large, all-carbon molecules, which came to be called fullerenes.
A molecule is not just when some atoms are stuck together by good bonds. There's another property of a molecule, and that is when you put the last atom, it kind of clicks and it's done.
It's stable.
And you offer it another atom and says, no, thanks, I'm happy the way I am. Well, that's what C60 was. We were offering it other carbon atoms in the apparatus we built, and it said, no, I'm going to stay with 60. So here's a molecule. At least it was a molecule in my mind's eye that seemed to explain the results, which has the most symmetry of any molecule ever discovered. It's a big thing. This is about a nanometer in diameter, about 10 angstroms here, a nanometer, a billionth of a meter.
In 1991, the significance of fullerenes gained even more momentum when Sumio Iijima, a scientist at the NEC Corporation, discovered yet another category of the cage-like wonders. But these fullerenes were slightly different. They were made of hollow molecules of pure carbon that formed a seamless hollow tube called carbon nanotubes, or in honor of Smalley's discovery, Bucky tubes. There's Bucky balls, right?
All right.
And then there's Bucky tubes.
Yeah, I've got These things get awfully big now. A tube of the diameter of this ball is this big. And this is a fullerene, same sort of structure. You know, here are the pentagons here, and there's the hexagons. There's 6 pentagons here, 6 pentagons there, 12 total. And in between all these hexagons, and now this thing is just a sort of a Bucky capsule, but you can imagine this thing being very long. And in fact, these things have been made millions of times longer than their diameter now. And these objects have incredible properties.
Like what?
Well, for one thing, if you, instead of holding this plastic object, which I can easily rip apart, if you held a Bucky tube in your hands and you go to pull it, you'd find it is the stiffest object in the universe.
Stiffer than steel.
Stiffer than steel.
Stiffer than diamond?
Stiffer than diamond. But you're a big guy, you can pull it. You'd find that you can stretch it out quite a bit before it breaks. And we'll find that it's 100 times stronger than steel in tension. The strongest fiber that you can ever make out of anything, ever. That means like a million years from now, when you ask me what's the strongest thing, same thing. You know, something has to be the strongest of all possible objects. This is it. And it's just carbon, so you could take coal or sewage or old rubber tires and convert them into Bucky tubes. Think what we could do with that. So we could rewire the world. We can make electrical cables that conduct electricity better than copper at 1/6 the weight.
So when you think about this, does it seem too good to be true? Does it seem magical or something?
It does. It does. I mean, how was the chance that you can discover something like this? But that's one of the fascinating things about the current status of our understanding of chemistry and physics. In fact, we can calculate the behavior of things very well these days. The big mystery with Bucky balls in these tubes is not that they would be great if you could make them. It was finding out you could actually make them.
Carbon nanotubes are one of the reasons the word nanotechnology has become so well known. Some are describing it as a modern-day industrial revolution. Nanotechnology refers to building things from scratch, like this nanomotor. It's the ability to assemble the atomic and molecular building blocks of nature to create a new generation of products and applications that are stronger and more precise. Is this the next realm of chemistry? Is this the next thing in chemistry?
I'm glad to see you use the word chemistry about this, because that's really what this is. We can't afford to pick every atom up with our fingers and stick them in. We have to have the atoms self-assemble, and they have to come from some source of cheap atoms so we can make these efficiently. We have a name for that. We call it chemistry. Of course, these days we call it nanotechnology, but it's the same thing. We're after to make a structure of a particular exact form, to do it hundreds of trillions of times a second, low cost with no environmental impact, to give us an object that will allow us to do something technologically that we couldn't otherwise do. Making objects with, if we're really good, the ultimate level of finesse, the way nature has always built the molecules of living cells. We'll now do this everywhere.
So it keeps you coming to work.
Yeah. There's a certain romance about it.
It's taken only 2 centuries to go from a time when atoms were a mere hypothesis to the brink of being able to snap atoms and molecules together and build new technology with fantastic possibilities. And the great discoveries that we've just seen helped make it happen. Exploring beneath the surface of things, inside the realm of chemistry, and changing the world.